Now that we're familiar with trigonometry and how it fits into triangles, we are going to move towards trigonometry on the Cartesian plane. So just a quick recap, we always remember sa, ka, toa. So sine is opposite over hypotenuse, cos adjacent over hypotenuse, and tan opposite over adjacent. But let's have a look at what happens when we bring this triangle onto the Cartesian plane. The Cartesian plane is this set of axes that once we form some ordered pairs, we begin to see how things can react in a two-dimensional space. And when it comes to trigonometry, what we need to be familiar with is the fact that we actually work around this axis here in terms of degrees. Okay, so you can start here at the very first, let's call it at the x-axis here, and we would call it 0 degrees. I haven't moved anywhere away from the x-axis. Okay, what is super important is that we always work in an anti-clockwise motion or direction. So we are going to travel around the Cartesian plane in that anti-clockwise manner. Okay, then we are going to travel, if we go towards the first line here, that means we're going to hit 90 degrees. If we keep on going to the next line, we'll head towards 180 degrees, then 270 degrees, and then finally, if we go all the way around, we'll end up at 360 degrees. So trigonometry is cyclic, which means that it repeats, and on the Cartesian plane, it's going to repeat every 360 degrees. It's easy to know that each time we add 90 degrees, because remember these two axes, the x-axis and the y-axis, are perpendicular to each other. So all of these angles here are 90. Okay, another thing that we refer to often on this Cartesian plane is the word quadrant. So that the axes actually divide the Cartesian plane up into 4 quadrants. So again, we work anti-clockwise, and we start with quadrant 1. And actually what often happens is that we write that in Roman numeral form, so quadrant 1. Okay, it's not wrong if you write there quadrant 1, like a normal one that you know, but get used to the fact that you will often see these in Roman numerals. Okay, and then moving anti-clockwise, we head to quadrant 2, quadrant 3, and quadrant 4. So it's helpful to know that when we're talking about an angle in quadrant 2, then the size of that angle is somewhere between 90 and 180. And when we're talking about an angle in quadrant 3, the size of the angle is somewhere between 180 and 270. Okay, so now that we understand this quadrant notation, let's have a look at what happens when we pull a triangle like this onto this x and y coordinate plane. So what you'll see here is that we've drawn a triangle in the first quadrant, which means that this angle here, theta, is going to be an acute angle. And now we're going to try and link some of our information here to this angle. Okay, what I want you to notice first of all is that we still have a hypotenuse across from the 90 degree. We still have an adjacent side, and we still have an opposite side in terms of this triangle. Okay, but now that we are on the Cartesian plane, we are actually going to need to link these sides to the axes that we're given. So x and y become important now. So if you have a look at a point, for example, if we looked at this point here, it would have the coordinates x and y. Remember, all coordinates on the Cartesian plane are in that form. Okay, so that's a point in our triangle, and then it's almost like we drew this triangle in relation to those points, or that point. Okay, now what we want to do is we just want to link this x and y to something. So if you have a look at the adjacent side in this case, you'll see the adjacent side runs along the x-axis. So that can be our x length there. And then if you look at the opposite side, you'll see that runs parallel to the y-axis. So that's the y length there. Okay, and it makes sense if you think about it. If you measure the x-coordinates at this point and drop it down, that would be the same value that we're dealing with there for that side. And similarly, if you measure the y-coordinate here, that would be, the y-coordinate here would be the same as the length between this x-axis and that point. Okay, and then our hypotenuse works in a very interesting way. Because we could draw this arm here anywhere in this space, we actually can link it to a circle. And so on the Cartesian plane, we talk about x, we talk about y, and then the hypotenuse, now it gets known as r. So there we have it neatened up, x, y, and r. Now let's take a look at what our sine, cos, and tan ratios would look like on the Cartesian plane. So sine is opposite over hypotenuse. Have a look at that. Opposite over hypotenuse. Sine now becomes y over r on the Cartesian plane. Cos adjacent over hypotenuse. Here's the angle. Adjacent is x. Hypotenuse is r. So cos on the Cartesian plane is x over r. And finally tan, opposite over adjacent, opposite to that angle, adjacent to that angle. So y over x. So there we have our trigonometry on the Cartesian plane. Let's have a look at what happens when we start putting this triangle in some of our other quadrants. So here we have it. We've got this triangle here in quadrant 1. This triangle here in quadrant 2, quadrant 3, and quadrant 4. Have a look each time that the reference angle is actually coming all the way from the 0-degree line. Now you don't need to let that stress you out too much. It just helps us to realize that if it comes all the way from there, it means we are working with an angle that is bigger than 90 and smaller than 180. But when you focus on the triangles, you can use, in terms of the logic behind it, you can use this little angle here, and you can still work with opposite, adjacent, and hypotenuse, or in terms of this Cartesian plane, y, x, and r values. Okay, this is important because what people have done over time is they had a look at the x and the y axes. And what we know by now is that in the first quadrant, all x values are positive and all y values are positive. And so what they did was they said, okay, well then if we take a positive y divided by r counts as the radius of a circle. And so that's a length, which means it's always going to be positive. So we don't need to worry too much about the signs there for r. But what they did was they said, okay, positive y over positive r gives me a positive sine. Positive x over positive r gives me a positive cos. Positive, positive, again, gives me a positive tan. And so what they discovered is that all of the trig ratios are positive in this quadrant. Then they moved over to the second quadrant and they did the same thing. Have a look at what's happening here. The y values are positive because they're all above the line, but the x values are on the negative side there of the axis. So now when you start to work out sine, cos, and tan, you'll notice cos is negative because x is negative, and tan is negative because x is negative. So what they notice there is that sine is positive in that quadrant. And they carried on with this approach, and they found that in the third quadrant, tan was positive, and in the fourth quadrant, cos was positive. And this has been extremely helpful just to apply a general rule. If you're sitting with a tan of an angle that is somewhere between 180 and 270, you can know straight away it's going to be a positive value. When you combine all of this knowledge, it actually leads you to what we call the cast rule. Okay, and there are a couple of different ways you could remember it. You could simply remember that cast, C-A-S-T, starts in the fourth quadrant and works anti-clockwise, or you could say all stations to Cape Town, and there are actually a whole bunch of others. Maybe you can leave a comment as to how you remember the cast rule. But this rule helps us because if we look at it, have a look at a value in quadrant 4. If it's a cos value, we know it's going to be positive. But if it's sine or tan, it's going to be negative. That's what the cast rule tells us. So everything that is represented here is positive in that quadrant. In quadrant 1, all are positive. In quadrant 2, sine is positive, but cos and tan are negative. In quadrant 3, tan is positive, but sine and cos are negative. And in quadrant 4, cos is positive, but sine and tan are negative. Let's have a look at some examples now. In which quadrants does theta lie if tan theta is less than 0 and sine theta is less than 0? The first thing we need to do is just interpret the question. Okay, less than 0, if you start to think about what that means, numbers less than 0 are things like -1, -2, -3. So what they're actually saying there with this notation is that it's negative. Tan is negative and sine is negative. So now we start thinking about the cast rule, because that's the rule that tells us where trig ratios are positive or negative on the Cartesian plane. So let's take a look. According to the cast rule, all values are positive here in quadrant 1. So that doesn't apply in this case. We want a negative tan. So having a look, in quadrant 2, sine is positive, but tan is negative. So that is a potential contender there. In quadrant 3, tan is positive, so that's not going to work. And in quadrant 4, cos is positive, but that means that tan is also negative there. So we've got two options, either quadrant 2 or quadrant 4. Let's have a look at that second bit of information that we've been given. Sine is negative. So again, we start here at quadrant 1. Sine is positive here, so that's not true. Quadrant 2, the S means that sine is positive here too, and we want a negative sign. Quadrant 3 has a T, tan is positive there, but sine would be negative. And quadrant 4, cos is positive there, but sine would be negative. So where both of these criteria are true, that is the answer to our question. So this is true in quadrant 4. Let's look at another example. Tan theta needs to be greater than 0. So greater than 0 are numbers like 1, 2, 3, 4, 5. Those are positive numbers. And cos theta needs to be greater than 0. So those are also positive numbers. Okay, following our cast rule, it's really nice and easy when they must be positive, because that just means we need to look for the letter. Where we see a T, that's where tan is positive. So tan is definitely positive there. And remember that all values are positive in quadrant 1. Then cos is positive, definitely in the C quadrant, and all values are positive in quadrant 1. And where I see both ratios meeting the criteria, that's the quadrant that it is going to be true in. So tan is positive and cos is positive in quadrant 1. Now sometimes what they like to do is combine the size of the angle with some information about a trig ratio. So now we need to go back and we need to remember how the sizes were allocated. So we started at 0 and then we added 90 each time. So 0, 90, 180, 270, and then all the way around to 360. Okay, and then if they tell us that the angle is somewhere between 180 and 360, well, this is where 180 starts, and then it goes all the way up to 360. So it's one of those lower two quadrants. And then they say to us cos theta is smaller than 0, so that means it's negative. Okay, where is cos theta negative? Well, it's where we don't see a C. So not here or here, because this is everyone's positive here. So it's either going to be one of those two, so there or there. And where both criteria are met, that's the quadrant we're talking about. So therefore, quadrant 3 for that one. And then finally, tan theta greater than 0, and theta is somewhere between 90 and 270 degrees. So if we take a look at that, let's again just see how the quadrants are divided. So 0, 90, 180, 270, all the way around to 360 again. And we know that we want something where tan is going to be greater than 0. Greater than 0 means positive. So positive tan is either going to happen here where all are positive or we look for the t because that is our sign that tan is positive. So tick and tick. And then our second little set of criteria there is it's somewhere between 90 and 270. So 90 starts here and 270 goes to there. So it's somewhere here in one of these quadrants. So tick and tick. And it looks like it's going to be quadrant 3 again. Okay, so basically you're given two sets of information. You need to remember this cast rule and then you can solve